Hello and welcome to our Chapter 7 video lecture series. In Chapter 7, we're going to be looking at two different types of hypothesis tests. One of them is called the chi-squared Goodnessoffit and the chi-squared test for association. Okay, so in Chapter 7, we're going to focus on analysis of categorical variables that can be separated into different categories. So we're looking at not means, but more like proportions. In chapters 6, really chapters 4, 5, and 6, we looked at two proportions, one proportion, two proportions. And in chapter 7, we're going to look at 3 or more proportions, and then also at more than one category. So we're going to look at, as I said, those two different hypothesis tests. Chi-squared, this is a Greek letter, so pronounced chi-squared. It's spelled C-H-I in English, but kind of looks like a scripty X. So like I said, the chi-squared Goodnessoffit, this is chapter 7.1, and then the chi-squared test for association, 7.2. So Goodnessoffit test says, basically, we're looking at, do observed counts agree with some claimed distribution? And then we'll look at chapter 7.2, the test of association hypothesis test, looks at, is there some association between two different categorical variables? And in these video slides, we'll go over kind of the one example of each of these, and then we'll look at the chi-squared distribution. Okay, so I want to take first example to look at before we get into chi-squared. Let's suppose you and your friend are having a very heated debate on your favorite fantasy series, and your friend claims she thinks that SRJC students prefer equally the series Harry Potter, Game of Thrones, and Lord of the Rings. So how can we test this claim? All right, so if we just had two different options, say Harry Potter and Game of Thrones, we could do a difference of proportions. But here we've got 3 different categories. So we can't really do difference of proportions, so we'd have to do really 3 different comparisons of difference of proportions. So one way to get around that is to look at this Goodnessoffit test. And just to let you know, you guys did a survey on this information, and I'm going to show you your class counts for these in a moment. Okay, so a Goodnessoffit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. All right, so we got some new notation here. O is for observed frequencies, capital O. Capital E we're going to use for expected frequencies. K is going to represent the number of different categories or outcomes, and N is going to represent the total number of trials. Okay, so I want to look at all right, here are your results for these 3 different options. 5 of you preferred Game of Thrones, 13 said Lord of the Rings, and 8 said Harry Potter. It's very interesting because in the past, usually Harry Potter tends up winning this, but your class tends to prefer Lord of the Rings. So here for observation, that's the observation. And we're going to use, as I said over a second ago, capital O is for observation. Expected counts, we're going to use a capital E. All right, so here I want to know K is the number of categories. We have 3. And N is the total number count. So that'd be 5 plus 13 plus 8, and that is 26. I'll write this in here as well. So we have our number of categories, 3 categories. Total sample size is 26. Our observed counts, and we're going to go through in a minute. And I'll explain how to calculate expected counts. All right, so we need some requirements. Oh, sorry, excuse me. Requirements or assumptions for this Goodnessoffit test. The data has to be randomly selected. All right, that's a problem with our class. We are not a true random representative sample of all of SRJC students. So we're going to ignore this for the first example, but in practice, you'd want to get a truly random sample. The sample data consists of frequency counts for each of the different categories. So we have that. We have 3 different categories in the one categorical variable of fantasy series. For each category, the expected frequency is at least 5. All right, so I'll note here the expected frequency for categories is frequencies that occur if the data actually has the distribution that is being claimed. There's no requirement that the observed frequencies for each category must be 5. So what I mean by that is if you're pulling data, if you have 2 or 3 in one category, that's not necessarily bad. The expected counts have to be at least 5. Again, I'm going to come back to this with the fantasy series example momentarily. The test statistic, I'm going to calculate this for our one example in a moment. But chi-squared, if you take this, it's the difference between observed and expected counts squared, because we only want positive values, divided by the expected counts. So the idea is how far off are the observed from the expected counts relative to what we expect to happen. And then this big sigma notation, this big E, so S notation, is to add up all those values. There are k-1 degrees of freedom, where k is the number of categories, and Goodnessoffit hypothesis tests are always right-tailed. If the observed and expected values are close, the chi-squared test statistic will be small and the p-value will be large. We'll fail to reject the null. The idea is if our observed and expected aren't too far off, then the assumption about the distribution is correct, or likely correct. Whereas if the observed and expected values are very far apart, the chi-squared test statistic will be large and p-value will be very small. We're going to reject the null hypothesis. All right, I'm going to show the chi-squared test statistic, the chi-squared distribution in stat key after we go through fantasy series example. But the chi-squared distribution is not symmetric. And hopefully this makes sense. We're squaring the difference between observed and expected, so we're only going to get positive values, or 0 possibly. It's not symmetric. It's always positive. As the number of degrees of freedoms increases, the distribution becomes more symmetric. So we're just going to have, in our example, 2 degrees of freedom, which is k-1. So this chi-squared is going to be a right skewed distribution. If we had a lot of categories, if I listed out, here would be 21 different fantasy series, we'd get more of a normal shaped curve. Again, not exactly normal, but more normal shaped. And here I've just put a flow chart kind of similar to all the p-values and test statistic we've been doing all semester. I should say the second half of the semester. We're going to compare the observed counts from the expected counts. If the observed and expected are close to each other, we're going to get a small chi-squared value and a large p-value. We will not reject, and we have a good fit with assumed distribution. If we get a large chi-squared value and a small p-value, we reject the null. If the p-value is low, the null must go, and then we do not have a good fit with the assumed distribution. Okay, so I want to go through, as you're right, about SRJ students equally preferring Harry Potter, Game of Thrones, and Lord of the Rings. All right. Okay, so I'm going to make this a little bit bigger. All right, we have all the information here. I want to put this in a different color. For Goodnessoffit hypothesis test, we always assume the distribution fits. some assumed values. And the alternative hypothesis is that at least one proportion differs. So I think it makes more sense. Hopefully that'll make more sense when we do this example. I'm going to let P sub G, let's see, I'll use a capital G here, equal the proportion of SRJC students who prefer Game of Thrones. I'm going to let P sub L equal the proportion of all SRJC students who prefer Lord of the Rings. And I'm going to let P sub H equal the proportion of SRJC students who prefer Harry Potter. So here I'm defining all of my population parameters. My null hypothesis in this case, we're going to assume all three of these are equal. And notice I have three different categories. We're assuming that SAG students overall prefer these fantasy series equally, so that should be a third. So we're not always going to assume the proportions are all equal for Goodnessoffit. In this case we do, because we're testing the claim of whether SAG students prefer these series equally. And the alternative hypothesis, I'm going to write more in English. At least one of these proportions is not 1/3. So notice right here, if we reject the null hypothesis in support of the alternative, I can't say more students prefer Lord of the Rings, even though that's what happened in our sample. All I can say is at least one of these proportions is not 1/3. So I'll go over this again more so when we meet in class, but the null hypothesis is, I call this a strong null hypothesis. This is saying a lot. All these proportions are equal, but the stronger the statement the null hypothesis gets, the weaker the alternative. At least one of these proportions is not 1/3. Can't say much, unfortunately, if we do reject the null hypothesis. All right. Okay, so I want to calculate expected counts. We assume the null is true, that 1/3 of SRJC students prefer these series. Right? And since the sample size is n equals 26, the expected counts for each category, in this case fantasy series, is, it should be 1/3 times 26. And that is, I'm going to approximate this to 2 decimals, about 8.67. So let's think about this. We have the observed counts, that's what you guys picked. The expected counts, if these are equal, they should all be the same value. And equally, sample size 26. If we do many samples around campus, more often than not, we should get the expected counts to be the same. Again, assuming the null hypothesis is true, that all these proportions are equal. Okay. The test statistic is chi-squared is the sum of the observed, observed minus expected squared divided by the expected. All right, in the next video, I'm going to go over how to calculate the test statistic for this example.